All right, put it down, flip it over, and I'm gonna quiz you. Okay, this is how we memorize things. Okay, I'll just say something and you say the answer out loud. All right, cos of 0. Good. Um, cos of 90, cos of 180, cos of 270, cos of 360, sine of 0, sine of 90, sine of 180, sine of 270, sine of 360, cos of 270, cos of 270, 0. Good. Sine of 90, sine of 270. Okay, cos of 90. Good. All right, folks, this is how we memorize things, right? So some people are like, oh, I have trouble memorizing. Well, this is what you do. Excellent. Good. Okay, so yesterday, we talked about the parent functions of sine and cosine. I did show you the parent function of the tangent ratio, and we decided, of the tangent function, and we decided that it's too ugly for grade 11, so we're not going to do it, right? You get to do tangent ratio in grade 12 with some really cool asymptotes, a lot of them. Do you know how many? Really an infinite amount. All right. So now that we know the parent function, let's transform the parent function. Sorry for being late, Miss Sly. Thank you. Get your book out right away. Okay. Anyone else here that I should? Don't worry. When I record, that page that I just showed doesn't show up because I would have to have switched it. All right. So today we are going to explain the effects of stretches and translations. So we're going to look at how various transformations will change the sine and the cosine function. We are going to relate the value of A. So what does the vertical stretch do? And we're going to connect it to the amplitude. Oh, we're going to look at what K does. What does the horizontal stretch do? And if the vertical stretch affects the amplitude, what does the horizontal stretch affect? The period, right? Usually, the sine and cosine function have a period of what? 360. But if I'm stretching it twice as much, what's the period become? 720, right? So we can change the period by changing the K. We can change the amplitude by changing the A. Okay. We are going to look at C, so the vertical translation, and that moves the central axis, right? Remember we talked about the central axis, the middle line that goes through the curves? Well, that we can move with the C. And then the last one that we're going to look at is D. That's the horizontal translation, and we give it a new name. We give it a name of phase shift. So yesterday when I was saying, how do you get the sine curve to be like the cosine curve and vice versa? And we were saying, hey, there's a difference of 90 degrees, right? So isn't D 90 degrees? Isn't it a horizontal shift? Well, we actually are going to call it a phase shift. Okay. And then we're going to use those 5 key points that we learned yesterday. We are going to use mapping notation to draw the transformed function. So it's kind of nice that we are coming back to what we did in units 3, 4, and 5 with mapping notation. It's kind of like a nice review as we get ready for exam review. At the end of this lesson, there is a question in which I give you a graph and we determine the equation. I'm going to leave that until tomorrow. This is a loaded lesson. There is a lot. It's 3 pages long. So I'm going to leave that one piece for tomorrow. So let's just get ready for this lesson. Okay. I could feel a few people are checked out. A few people are tired. So let's do a few exercises. First thing we're going to do is we're going to actually relax our eyes. So take the palms of your hands and just put them on your eyes. So it's pitch black inside. Keep your eyes open. Okay, talking doesn't help because you need those muscles to really relax. Okay, and so if your eyes are open, they are using the minimum number of muscles. Okay, just keep them open and you're actually allowing all those tiny muscles in your eyes that work so hard during the day to relax. All right, take your hands off. Now, let's give your face a nice massage, rub your eyes, rub your forehead. Like there's so many muscles there. Okay, especially here. Who grinds their teeth when they sleep? Anyone? Okay, so this is the TMJ muscle. Okay, you really want to relax those. Relax your cheeks. Kiara, sit down. We're doing a massage. Okay, now there are muscles that go along your chin here. So you know how when people get old, they get like wrinkles and stuff? It's actually because those muscles tighten. So you want to, along your jawbone, you want to just do these circles and relax those muscles. Okay. Get your neck a bit. Okay. Roll your shoulders a bit. Okay. Those who did it, I feel better. I hope you feel better, a bit more awake. All right. Good. So let's get down to business. We got a lot to do. I want to encourage you to stay focused, stay engaged. Okay. Because it's a big lesson, right? So I would say half of the quiz is on this, right? And then half is on the other two lessons. Yes, the quiz is on Monday. All right. So let's first of all recall this function notation, right? This equation, y equals a f of kx minus d. Remember, we call this function notation because there's the symbol of the function in there. So it's not the equation, it's just telling us just the transformations. And whenever you write in function notation, you must have, in addition, you must have an equation that actually tells you the parent function. Okay? This information is only transformations. So let's review what each of these transformations do. Oh, that's not the color. What do we call the A? Vertical stretch. But also what else? What else can A do? A is the one that has the double. Yeah, in which axis? Beautiful. Reflection. I hear some people eating. If that's something that's going to help you stay awake, feel free to get a snacky out. Reflection in X axis. Okay, if you have water, that's another good thing. Okay. Let's make a note that if A is less than 0, so if A is negative, we reflect. And if you want to write flip upside down, fine. If A is greater than 1, it's a stretch. If A is between -1 and +1, right? So it's a decimal, it's a compression, a vertical compression. What's up?
So we flip only when A is less than 0?
Yes, if it's negative, you flip.
But if it's 2, it will stay like 2 again.
That's right. That will just be a stretch. All right, K, that was the new one for this year, right? This is our horizontal stretch. And what else is it? Good. It's a reflection in the y-axis. So let's talk about that. If k is less than 0, so if it's negative, okay, we reflect. And this is the one that which axis is the monkey bar around which the function spins? The y-axis, right? It's like you're spinning sideways. So we're reflecting in the y-axis. And then this is the weird one. How did I write this down? Compression. Okay, so the stretch factor, how do we find out what is the stretch? This is the weird one. What do you do with the k?
You inverse it?
Good. It's not inverse.
Oh, yeah.
What's the word? What's the word? Reciprocal. Good. Inverse means undo. It's the control Z. Yeah. So we figure out the stretch factor by finding 1 over k. Okay, and then we have the nice and easier ones. We have the D, which is the horizontal translation. I'm just going to write horiz translation. And we remember that if it says x plus 4, that is 4 in which direction? Left. And if it says x minus 3, that's going to be 3 in which direction? Right. So everything related to the horizontal movement, the horizontal transformations is always a little messed up. Vertical, nice and easy, simple, as it is what you see. All right, and then the last one we have is C, which is our vertical translation. Vert translation. And this one is as we see it, right? If C is 2, we shift 2 up. Does anyone remember the order of transformations? Beautiful. Let's write that down. Order of transformations. Does anyone know what I did with this N? Do you guys know that short form? That when you write, like, if you have shuns, you write T, and then this N, like as a superscript with an underline, is actually ION, right? It's a nice short form. Order of transformations. R stands for what? Reflect. S stands for? T stands for? What is it? Translate. Good. Okay, so first flip, then stretch, then translate. Now, which of these two can you change the order and it's still the same thing? R and S. It's like in BEDMAS, you can do division and multiplication in whichever order it comes. But then the translation is separate, right? That absolutely has to be the last step when we're graphing. All right, so for example, when we have a sine function, 3 sine 2 x minus 40. So notice, why is 40 written as 40 degrees? Why is it? Yeah, so the 40 is alluding to the horizontal shift, which we're going to start calling a phase shift, right? It's talking about how much the function is moving left or right. And the axis, the horizontal axis, is now being measured in degrees. So the x-axis is your angle. That's why now our equation has an angle, and you must include that degree in there. And if we were to do it in radians, you wouldn't write radians, but you would write it in radians. Now, we are not doing radians. So if we have this equation, okay, let's talk about what type of transformations we have. So let's start with the R. Are there any reflections or in either axis? No reflections. And I'm going to say why. Since A and K are greater than 0. Let's talk about the easy stretch first, the vertical stretch. What type of vertical stretch do we have? By 3. Vert stretch by 3. Now, I want to relate it to the terminology we've been using in this unit. Anyone remember what is affected? What does the A change for the sine and cosine function? Yes, but remember when we were talking about the periodic functions? The amplitude, exactly. So this directly changes the amplitude. So now amplitude is 3. Right? If the amplitude for the parent sine and cosine function is 1, and we're going to multiply it by 3, well, the amplitude becomes 3. Well, we have another stretch, and that's the horizontal one. Now, let's think about this. Is it going to be a horizontal stretch or a horizontal compression? Good. By what? Did you say 1.5? Just 1/2. Yeah, 1 over K, 1 over 2. Okay, so we have a horizontal compression by 1 over 2. Right? If you need to, label the K in the equation. Or I guess I could have done that. Label the A. And so if our K in the equation is 2, that means that the stretch factor is 1 over 2. And that means your function is going from being this wide to half as wide. So what does that affect? The period. And what does our period become? Beautiful.
Besides,
Yes.
you said that we have 1 over k only when k is less than 0. Or 2.
No. When K is less than 0, we have a reflection in the y-axis.
Okay.
The stretch factor is always 1 over K. Yes? We will get into that. Yeah, that will sort of be like a regular thing, that we will be using terms like amplitude and period as opposed to saying like the horizontal stretch. Yeah, for sure. Because I will even ask you questions. What is the period? What is the, yeah. And we will do some word problems and that kind of stuff. All right, so the period is going to be 360 degrees times 1 over K, right? Because the period of the parent function is 360. So you always take 360 and you multiply it by 1 over K to figure out the new period. So in this case, we're multiplying it by half. So the period is 180.
Sorry, why did you multiply it by 360 and not, for example, 40?
Good. So 360, as we saw yesterday, is 1 period of the parent cos function. And same for the sine function. 1 period, remember, 1 period is the length of the cycle. So when the curve starts repeating, it takes 360 degrees. So for a parent function of sine and cosine, you need to know that the period is 360. Okay, and now we go to the t's. So we have a vertical. Do we have a vertical translation? Yeah. How are we moving? Up, down, how much? Up 4. Good. 4 up. And anyone remember which characteristic of the sine cosine function this changes?
The central axis.
The central axis. That's the axis in the middle. All right. So the central axis. Now we give it an equation, right? Because it's a horizontal line. So since it's a horizontal line and the y values do not change, we say y equals. Remember when we had asymptotes and you had to write the equation of the asymptote, and the horizontal one was y equals and the vertical one was x equals. Okay, and then we have one more translation, and that's the horizontal translation. And this is a weird one. It's 40 degrees to the right. And so we call this is where I'm going to bring in the terminology of the phase shift. Okay. And we call it, this is how we name it. It's a 40-degree phase shift. To the right. Okay, so there can be various phase shifts. This one is a 40-degree phase shift. All right, so let's summarize what we've got. Okay. So let's see how these transformations are going to affect the sine and cosine function. So we know, I'm just going to put some check marks here, but you have this table here. So the amplitude of the parent function is 1. Well, the amplitude, once we have a vertical stretch, the amplitude becomes a, straight up like that. The period of a parent function is 360, and the period becomes 360 times 1 over k, which is actually just 360 over k, right? Central axis starts off as y equals 0. And if there is a vertical translation, the central axis becomes y equals c. Okay, and then the effect of parameter d, the horizontal translation, is d units to the right because we have a periodic function. So the phase shift is not just for a sine or cosine function, it's for any periodic function. Okay, and for periodic functions, we call it a phase shift instead of a horizontal translation. Okay, lots of new words. So let's look at an example. All right. Yes. Yes. You would say, if there was a phase shift to the left, you would say it's 40-degree phase shift to the left. Yeah. So you always actually have to give the direction. Two functions are graphed below. And these are the base functions or the parent functions of y equals x, of y equals sine x and cos x. So first of all, let's label them. Okay, so you know them now. Which one is which? Think about it. Look back in your notes if you need to. Kotreia, kotreia. Nikeia sine, nikeia cos. All right, so we've talked about this yesterday, folks. What transformation must be done to transform the graph of cos x to the graph of sine x? So we're starting off with cos x, and we want to make it identical to sine x. Okay, so I want you to try this out. Like you're literally going to shift it over left or right, and you're going to use the word phase shift. Okay, so try writing something. Don't worry if you get it wrong. There's a lot of space there. So I'm choosing one key point. So maybe for the cosine function, I'll choose the peak. And I'm going to look at what is the horizontal difference between the peak of the cosine function and the peak of the sine function. How many degrees between them? 90. And because we are transforming cosine into sine, we're moving it to the right. So it's a 90-degree phase shift to the right. Very similarly, now we want to, which transformation must be done to transform the graph of y equals sine x to the graph of y equals cos x. So now sine wants to be cos, right? So I'm going to choose a different point. I might choose like a valley or a trough. And I'm going to say, okay, this one wants to go there, right? It wants to shift over there. How much is that? Well, what do we know it is? It's definitely 90. Okay, so it's a 90-degree phase shift to the left. Now, let's write some fun, yeah.
Does it matter if we say 90-degree phase shift or phase shift 90 degrees? It's the same thing.
That's cool.
Okay.
Yeah. All right, folks, let's actually write some equations. Okay, so we've got, we've got y equals sine x. How can I write it? How can I write cos to be identical? Okay, what do I have to, we already said we have to add a phase shift of 90 degrees. So watch this. Where does the phase shift go? Well, it goes in the location of D. And because it's to the right, so sine x equals cos of x minus 90. Now, using this example, write an equation for part C. It's going to look really similar, except that we're equating it to cos. What do I add? Plus 90, right? I'm going to the left. Dudes in the back. Thank you. Okay, so now we're getting comfortable putting a phase shift into our equations. Don't you feel all grown up? Like you thought that doing like regular transformations was a big deal. Now you're throwing in a phase shift and you're like, yeah, I got this. All right, excellent. Example 2. The function f of x equals cos x is transformed to the function g of x equals a cos kx minus d plus c. First of all, state the range. So range again is like this. Okay, range of parent. Let's make a note. Range of f of x. Right, that's the parent range. Well, we know that a regular cosine function goes, it's continuous, and it goes from -1 to +1. Right, like that's what we know. That's our baseline. Sorry. Feeling kind of forest green. Else would match mine. All right, we're good with that. That's the basic range, right? We're talking vertical. So now, which two transformations are going to affect the range? A, K, D, C. A and C, right? K and D affect horizontal stuff. And so what that means is that the range of G of X is going to be still continuous. Y belongs to all real numbers, but now we have to change the range. And this is how we do it. Well, we have -A plus C. Oh, I need more space. -A plus C all the way to +A plus C. Let me zoom in on that. So the -A tells us sort of how low we go, but then we have to add the vertical translation. So notice there's no -C in this. Okay, you're always shifting the same amount up or down. It's just that the stretch will stretch you out in the negative direction and it will stretch you out in the positive direction. Okay, so we first change the amplitude and then we move the central axis. The domain on the first cycle is x belongs to R, between 0 and 360, right? So that's the domain of the first cycle of f of x, right? Because the period is 360. Okay, well, what's going to be the domain of the first cycle of g of x? Because g of x has a k value and it has a d value. So we're going to be stretching or compressing horizontally, and we will be having a phase shift. All right, so the domain, we can get the first part, right? X belongs to all real numbers. Now, when we are finding the domain, we start off with the original value. So if the parent function starts off with 0, we are going to map it. We're going to use mapping notation to figure out what we get. And on the other end of the domain of the first cycle is 360 degrees. Again, horizontal phase shift divided by k. This one, again, horizontal is always the trickier one. Now, this would change if I said on the first two cycles, right? Then we're punching in 0 to 720. How are your brains doing? Do you need a 1-minute brain break? Or can we do the next question? Folks, tell me, did I fully lose you? Who needs a brain break for 1 or 2 minutes? All right, and then we'll continue. Catch my mistake. Yeah, exactly. We talked about RST. We talked about doing reflections and stretches. Oh, sorry. All right, folks, come back here. Bring your brain back to this room, to this peaceful, tranquil sanctuary of math that you will miss so much next year. All right, yeah, so this is the mistake. If we are supposed to, do a stretch and compress before any kind of shifting or translation, this is not correct. Because if I use this fraction, what's the first thing you're going to do? Plus d or divided by k? Using this fraction, I would first be adding d, right? So that's how some of the students were like, yeah, Miss Slide, that doesn't look good. And that is correct. It doesn't look good. So what we want to do is we want to take the fraction away from the entire section and add it like that. Now, in this case, 0 divided by k would still be 0, right? So we could really say that the domain would start at D. Does that make sense? Do people see the mistake I made? Were they able to correct it? I apologize. I really try not to make mistakes, but they do happen. Now, here's another question that I had. Someone was like, yeah, but Miss Sly, I thought that the periodic functions are that they just go forever and ever, that they don't stop. So what were the key words that are telling me that I need to restrict it? More. No. Yeah, more, not just cycle. First cycle. So the first cycle is, I'm going from 0 to 360 and I need to transform that. What if I said, what are the restrictions on the second cycle? Where would you start at and go to 720? All right. Let's do a question. Sketch the function, okay, y equals cos x plus 90 plus 1 for 0 to 360. So here I am restricting what you draw. You will not draw a continuous function forever and ever, and you will not include any arrows. State the amplitude, equation of the central axis, period, and phase shift. All right, well, let's start off by writing down what are our A, K, Ds, and Cs. A is 2. K, there is no K, so we just say it's K equals 1. D, what's D? Negative 90 degrees. And C is positive 1.
Can I open some water?
Go for it. Whenever we need to draw a transformed function, we need to start off with the parent function. And because we're going to be doing mapping notation, we are going to be transforming key points. So our parent function is y equals cos of x. And here's another opportunity for us to memorize 5 key points. Okay, so when x equals 0, 90, 180, 270, 360. All right, go ahead and fill in the y values. Dudes in the back. Good. I'm glad. I like that I'm seeing people referring back to the other page. Excellent. Okay, let's get going. Let's do some work with the transformed function. So we need to think of our mapping notation. Okay, so we're gonna get, excuse me. We're gonna get 0 divided by k plus d. So we've got, let's actually write this down. So we're gonna have x minus 90, right? Because there is no k. But for y, we have to multiply it by 2 and then add 1. So here we have our mapping notation. And so remember how we use the key points and we substitute them into the mapping notation to find our transformed function. So 1 point at a time. 0 minus 90 is negative 90. 1 times 2 plus 1, well, that's 3. Okay, go ahead and do the rest of the points. Is this coming back a little bit? It's kind of nice that we end up reviewing a lot of what we have done. So as I'm looking at these transformed points, I notice a few things. I notice that I'm still going up by 90. And that's because I'm not stretching or compressing horizontally. And then I'm noticing the new maximum values. What are the new maximum values? 3. And the new minimum is, and in there, what is the central axis going to be? What's the value? Y equals what? 1. Right? So whatever the zeros used to be, well, now it's a 1. That means the central axis is a 1. Okay, so let's graph this function. Now we can't graph the first point because we are not given that on the graph, right? So if the graph stops at 0, you're not drawing anything before. Okay, so I've got at 0 degrees, I've got 1. So let's see, are we going up by 2s? 1, 2, 3, 4. Yeah. So at 0, I'm at 1. At 90, I'm at negative 1. At 180, I'm back to 1. At 270, I'm back to 3. 1, 2, 3. And I stop. And now we're doing straight lines. Oh, dang. Excuse me. Okay. So watch. We have to graph between 0 and 360. So I'm missing 1 point, right? I can't stop at 270. Can you make an educated guess? What will be the value of y at 360? Okay, we're not sure, so let's draw what we've got. Oh, this is such a big curve. It's so, okay, wait, nice and smooth, Miss Sly. So it's just a really wide axis. This is not a horizontal stretch. It's just that the axis is so wide. So think about it. If I'm going another 90 degrees, where will I end up at? Okay, if we're not sure, let's actually put one more point in. It is 1. Yeah, because it's just 1, it's just 90 degrees. No arrows, because we are restricted to just draw it between 0 and 360. And we've been asked to state certain characteristics. How do I find the amplitude? Well, the amplitude is just the value of A, right? Amplitude equals A equals 2. Period is trickier. We go 360 divided by K, which in this case is 360. We need to find the phase shift. That is your D. So our phase shift, now watch this. You're not going to say it's negative 90. You're going to say 90 degrees in which direction? Left. Good. So that negative is 90 degrees to the left. What else am I missing? Period, we got. Central axis. So I've used AKD. Now I need to use C, right? So I know that central axis is Y equals C. And so in this case, the central axis is at 1. And we kind of guessed that from seeing that the function was oscillating above and below 1. All right, folks, you drew your first transformation. Da-da! All right, shall we do another one? No. Shall we? Yes, Miss Sly. Can we do 2 more? Maybe. Yes. Go back. All right, look at the next question. What is the trick? Oh, yeah, there is a trick. What? Yeah. So mean. Anyone see the trick? Ooh, dang, yes, we got a common factor. All right, we have to common factor inside the brackets. Okay, that is the trick. We will not be tricked. So we must factor out the 1 over 2. Okay, so that's a bit tricky. If you need to use your calculator, then do it, right? 90 divided by a half is not the same thing as 90 divided by 2. When you divide something by a half, it actually gets bigger. X minus 180, right? Again, we are told to draw the function between 0 and 360. All right, so I have my A is 3, my K is 1/2, my D is 180 positive, and my C is negative 2. What is the parent function? Yep. Okay, so let's remember, what does our sine function look like in its parent form? Okay, so fill that in. What's up? Yeah. And then I want you to attempt the mapping notation. Okay, really good chance to remind ourselves how to do this. So mapping notation. Oh, this is tricky. So we're going to have x over k over 1/2. But what does that look like? 2x.
Because we just say k equals 2.
It doesn't. It doesn't equal 2. The horizontal stretch factor is 1 over k. Horizontal stretch factor is 2, but k equals 1/2. All right, you can do this. Right? Let's transform every point using the notation. Oh, yeah. Ooh, thank you. Is that what you were going to say, Marley?
Yeah.
Yeah. Thank you. Plus 180. Okay. Okay, so go ahead and you do the transformations yourself. Graph the function yourself. Any thoughts here as we're working on these transformations? Any feelings about this? I've got feelings that I don't want to do all this work if I'm not going to be plotting it. Would you agree? Yeah, like let's stop. This is nonsense. Stop. Why are we stopping? Well, we were told to graph between 0 and 360. So let's plot what we know. It's not much, it's something. All right, so we've got at 180, it's -2, and we're going up by 2s as well. So at 180, -2, -1, -2. And then we know that at 360, we're at +1. Folks, that is not enough for me to know how to graph, right? So now we have to think about the characteristics of this function. What is going to be the central axis? Pardon? What central axis is y equals c? What is my central axis? -2. Oh, yeah. This helps me because then it kind of gives me a sense, oh, we're oscillating. We're going above and below the central axis. What is my amplitude? What is it, folks? 3. Okay, so, and then we want to know what is my period. Okay, so what is my period going to be? It's going to be 360. I need more space. Period is going to be 360 divided by k, but because our k is 1/2, it's going to be 2 times 360. That means our period is 720. And so if our period is 720, we break up our function into 4 pieces. And that means that every 180 degrees, there is a change in the function. We get a key point every 180 degrees. So if I take my period, 720 divided by 4, I get 180 degrees. And that tells me that every 180 degrees, I get a key point. Every 180 degrees, we have a key point. We are going to use all this information to find the point that would happen before 180 degrees. All right, so let's walk through this. First of all, if the central axis is y equals -2 and the amplitude is 3, how low will the next point go? -5, right? So I know somewhere along this line, I'm going to get a point. Okay, next, I need to know where. So we said every 180 degrees, we get another key point. So if the last key point was at 180, where will the next key point be? Nope, take away 180 at 0, meaning this is my next key point. That is, I'll write it here, 0 degrees, -5. And so now we can draw the curve. Now it's hard to draw because you want to make sure you're not drawing a straight line, but it kind of curves. It's like a really long S. I will keep trying. I'm not giving up on you, curve. Okay, I told you it was heavy, right? One more example. And that's why tomorrow I'm going to do just determining the equation, and then we're going to practice. Okay, we're going to take the day to just review this stuff and practice it. All right, go ahead and look at example 5. Sketch one cycle of a sine function with a period of 1,800 an amplitude of 12, a central axis of y equals -4. And no phase shift, because they didn't say so. What's the first thing I can draw on the graph? The central axis. Yeah. So I chose blue because then I'm going to make it blue. So I know that the function will oscillate. It will go above, beyond. It's going to go above, touch, below, touch, above, touch. Now, I know it's going to go up until 1,800. And because there are 5 key points, watch this. I get key point every 1,800 divided by 4 degrees, right? So that's 900, 450. So every 450 degrees, I get a key point. So you have to take that period and divide it by 4 to figure out what are the 4 quarters of the period. Yeah.
Why do you even need this key point?
I'm not doing key points. Oh,
Why do you need time?
we're not going to use the traditional key points, okay? We're not going to do mapping notation. You could, but I don't think we need it because we know enough information now. Now, before we start graphing our points, let's actually put a line for the minimum and maximum. So if I look at that's a very good question. Why am I dividing it by 4? So if I'm looking at a parent function of the sine curve, it starts here, ends here. For one cycle starts here, ends here. Well, that cycle is actually can be divided into 4 quarters. And I think of a quarter as between key points. So between the first and second key point is this area. Second and third key point, this area, and this area. Okay, so I don't actually need to find the points anywhere between the key points. Put your phones away. Come on, dudes. Okay, I don't care about the points here. I know it's going to be curving up. Afterwards, it's going to be curving down. Okay, so the key points are where it starts to change or when it hits the central axis. So let's go back here and start with the sine curve. And we know, okay, so I want to draw the max and the min. So -4 plus 12 is going to be 8. And -4 minus 12 is -6. So I drew these just to give myself a sense of where to stop the function. Okay, the sine function starts at the central axis. So at sine equals 0, the sine function is at the central axis. Okay. At sine equals 1,800, at the end of the cycle, it is again going to be at the central axis. And one more location where it's going to be at the central axis. Where's it going to be? 900, right in the middle. So I just have to figure out the 450 and 1350, right? The two, which one is the max, which one is the min? So we think to ourselves, does the sine function first increase or does the sine function at first decrease? Which one is it? It increases. And so that means at 450, I have the max. And at 1350, I have the min.
So there can't be, for example, that 450 is 4.
Pardon?
There can't be, for example, that 450 will be 4. No, 8. No, only just. So why is it maximum value?
Oh, because what we know of the sine function is every second key point is at the central axis, right? So I know I have to go from central to either the max or the min. From central, either to max or min.
There can't be between.
Yeah, you can't have a straight line. Yeah. All right, folks, give your homework a shot. I know we're reviewing tomorrow, but please do your homework so we can make it even richer tomorrow. All right.